And the point is, at low densities, what happens is that most of the electrons get to have low energies, which they kind of want to have. But if you pack lots and lots of electrons together, all the low energy orbitals get occupied, so that most of the electrons are forced to sit in energies that are much higher than that. And the point is that those electrons have much higher kinetic energies than you would expect them to, based on the temperature. And so as the temperature rises, you hardly change the energies of the electrons because their energies are mostly due to the Pauli exclusion principle, mostly due to the fact that they're forced to have very high energies because all the low ones are taken already. And as a result of that, raising the temperature hardly does anything at all with pressure is what it comes down to. And that's the punchline, that under a case of degeneracy, the pressure no longer depends on the temperature anymore. Because unlike in an ordinary gas, when you raise the temperature, you make the atoms or electrons or whatever go significantly faster. That's no longer true in a degenerate gas. Raising the temperature does very little to affect the speeds of most of the particles, which means the pressure that they're exerting hardly changes at all when you change the temperature. So, is that good enough?
Mm-hmm.
Yeah. Any follow-ups on that? And the punchline is the pressure doesn't depend on the temperature in a degenerate gas. And that's what causes, for example, the helium flash, because when the nuclear reactions start in the degenerate core of a low mass star, the reactions add energy to the core and make it hotter, but the core can't expand and cool back down, so the reactions go even faster, which makes it even hotter, which makes the reactions go even faster, which makes the core even hotter, which makes the reactions go even faster, which makes the core even hotter. It spirals out of control because it's degenerate. If it weren't degenerate, the energy released by the reactions would cause the core to expand and not allow its temperature to rise, and then the reactions don't go out of control as a result of that. Yes?
So, do the increasing levels symbolize an increasing heat on those diagrams?
On these diagrams, these are increasing energies of the electrons. And the idea is that most of the electrons are forced to sit in high energy levels, much higher than you would expect just based on the temperature. Even at absolute 0 Kelvin, even if there was no extra thermal energy, whatever, it was as cold as you could make it at absolute 0 Kelvin, still most of the electrons would have very high energies because all the low energies are already occupied, and there's a rule in quantum mechanics that says only 2 electrons get to occupy a given so-called orbital, quantum wave function. And the analogy we made in class was, if you have a football field, you can think of like how high you are from the field as representing your energy, if you like, your gravitational potential energy. It really does. I mean, if you're on the field, you got to climb to get to a high level seat. You do get more gravitational potential energy by doing that. Everyone would like to sit, I'm pointing at the screen like you can see that, everyone would like to sit close to the field, or at least let's assume that they, but some people like sitting high, but whatever. Let's assume everyone wants to be as close to the field as possible. If there's only a few people in the stadium, everybody gets to sit down close to the field and gets a great view. But if it's sold out, then lots of people are forced up into the nosebleed seats. They'd like to be sitting down here, but those seats are already taken. And so, because people won't allow other people to sit in their seat with them unless it's their kid or something like that, most people are forced to sit much higher than they would like. And it's kind of like what happens in a degenerate core. Most of the electrons are forced to much higher energies when they would, quote unquote, like to minimize their energy and be in the ground state, low down, but there's no room. It's already taken by other electrons. Yes?
Is the intensity pressure of the neutron is smaller than that of the electron?
No, it's the other way around. So we'll get to that in the next chapter, where we will see that neutron stars are supported by neutron degeneracy pressure instead of electron degeneracy pressure. And because of the greater mass of the neutrons, it turns out that neutron degeneracy pressure can support even more mass of the star. Even it can fight more strongly against gravity than even electron degeneracy pressure can. So neutron degeneracy pressure, if you will, is even stiffer than electron degeneracy pressure. It's stronger than electron degeneracy pressure.
So why is the neutron star smaller than?
Yeah, because it turns out that the neutrons, so when the core collapses, originally it's supported by electron degeneracy pressure. The iron core is supported by electron degeneracy pressure. But when the mass of the core exceeds what's called the Chandrasekhar limit, about 1.4 times the mass of the sun, that's the maximum mass that electron degeneracy pressure can support. It won't work anymore. And so the core starts to collapse because electron degeneracy pressure isn't strong enough. Now at that point, the star isn't made of neutrons yet. The core is not made of neutrons yet. It's during the collapse that electrons combine with protons to make neutrons and neutrinos. So now you get a bunch of neutrons, which when the core gets to about the size of a city, become degenerate. They're not degenerate until the core is that small. They become degenerate and boom, they keep the core from collapsing any further by exerting their very powerful neutron degeneracy pressure. Unless the mass of the core is bigger than about 2 times the mass of the sun, and then nothing can stop it, and it collapses all the way down to being a black hole. So that's the story of that. Yes?
On the other questions.
Okay, any follow-ups on that? Okay, yes?
Like what is an H2 region and what causes the ionization of the hydrogen?
Yeah, H2 regions are stellar nurseries. Cute little baby stars are being born there, except that baby stars are actually gigantic. So cute, gigantic baby stars are being born there. Aww. It's kind of right. Here's H2 regions, these pink regions. Don't you want to just go like, because there's all those little babies, big baby stars in there. So stars are being born there. And some of those stars are O and B type stars. O and B type stars, are they hot or cool? They're hot. So since they're hot, they give off a lot of short wavelength ultraviolet radiation. They give off lots of ultraviolet photons. And those ultraviolet photons have enough energy that if I got a hydrogen atom and one of those photons, the electrons aren't literally circling it, whatever. Here's an electron orbiting a hydrogen atom. It's really in a quantum orbital. One of those ultraviolet photons comes along and bam, it gives it so much energy that the electron is ionized. It's stripped off of the atom. So H2 regions are regions of ionized hydrogen. H Roman numeral 2 means ionized hydrogen. And the ionization is caused by ultraviolet light coming off of O and B stars that are being born in the H2 region, being born in the emission nebula. Emission nebula and H2 region are synonyms. They mean the same thing. Calling it an H2 region emphasizes that it contains ionized hydrogen. Calling it emission nebula emphasizes that such regions give off spectral lines of hydrogen due to recombination. It's why they are glowing. It's because of the fact that, okay, go back. There we go. Huh. It's all weird in terms of the colors now. All right, but it's not very interesting. Okay, so anyway, so any given atom, UV photon comes along, frees the electron. It's free, it's free, it's free. Here's a proton that lost its electron. When a proton meets an electron, they're like, hey, let's get together and make an atom. And so the electron can be captured into orbit around the nucleus to recombine with the hydrogen nucleus, with a proton. Typically, when it does so, it's captured into a higher energy orbital, not into the ground state. And then the electron can start dropping down to lower energy levels. And the spectral lines that are given off by lots and lots of hydrogens dropping down to lower energy levels is what's making it glow. we're seeing the hydrogen Balmer emission lines making it glow. So it glows due to recombination radiation, due to electrons being captured into high energy orbits, recombining with protons and dropping down to lower energy levels. But the reason they have to recombine in the first place is because ultraviolet light from hot O and B stars is stripping electrons off of atoms. So both processes are happening at the same time. Yes?
So these O and B type stars that are hot give off ultraviolet radiation.
Yep.
Does that cause the ionization?
That's what's causing the ionization, yeah. The H2 region is flooded by ultraviolet light from hot O and B stars that are being born within it. So then the hydrogen atoms are subjected to that ultraviolet radiation, and when those UV photons hit hydrogen atoms, they're absorbed, and the energy is used to strip the electron completely off of the atom. Yes?
And then the hydrogen emission lines are what causes the pinkish color.
Yeah, they are hydrogen emission lines because at the same time that some atoms are being ionized, other atoms are reforming. We call that recombination. The electron is combining again with a proton. It's recombination, and it starts out usually at a high energy level, and then it starts making downward jumps. And when it makes a downward jump, every time it does that, it gives off a photon. And the combination of lots of emission line photons from hydrogen atoms that are recombining in the H2 region combine to give it the pinkish color, just like in class when we had the hydrogen lamp and I turned it on and it buzzes and makes a pink glow. It's the same process going on. Spectral lines of hydrogen combining to look pink to our eyes. Yes?
I have a question related to.
Okay, anybody want to follow up with that question? Okay, fire away.
Could you explain strong nuclear force and how it relates to that neutron flow?
Yeah. So remember when we go with like the proton-proton chain. So we have that it starts with two protons, for example, smacking into one another and forming a deuteron. And ultimately, we end up with a helium-4 nucleus, for example. Okay, so look at this helium-4 nucleus is just an example. It's got two protons in it. Are those positive, negative, or neutral?
Protons? You say protons?
Yeah, protons. They're positively charged. What about neutrons?
Neutral.
Neutral, they don't have a charge. So electrically speaking, do the neutrons attract, repel, or neither to each other and the protons? Neither. Electrically speaking, they're neutral, so they're not attracting or repelling the protons or the neutrons. What about the protons? Are they attracting or repelling one another?
Attracting.
They're their same charge, right? And opposites attract, but likes repel. Yeah, so they're repelling one another. They're repelling one another. So, if all we were talking about was the electric force, nuclei would blast themselves apart because all those protons are repelling one another. So there must be some glue, if you will, holding the nucleus together. There must be something other than the electrical force operating in the nucleus, because otherwise the electrical repulsion between the protons would blast the nucleus apart. They would just fly apart. The strong nuclear force is the glue that holds the nucleus together. It's a very short range. The electromagnetic force extends out to infinity. Two protons feel one another's repulsion no matter how far apart they are. They feel it more and more strongly as they get close to one another. But the nuclear force only operates on scales, length scales that are about the size of an atomic nucleus or less. So it's a short range force, which means two protons that are a lot further apart than the size of a nucleus don't feel the attractive nuclear force. All they feel is the repulsive electrical force for one another. And this is the reason why it takes high temperatures to cause fusion in the first place. Protons repel one another, and so typically at room temperature or low enough temperatures, not stellar core temperatures, like even in the hot outer layers of the sun, it's not hot enough, the protons because they repel one another, even if they're headed straight for one another, the repulsion causes them to stop and turn around before they get close to one another. But if they're moving fast enough, because the temperature is high enough, they can get so close to one another that they're able to feel the strong nuclear attraction force for one another, and that's why they can stick and fuse with one another. It's because they can get close enough for the strong nuclear force to be felt. That attracts them together, and it also turns out, because of the nuclear physics, it turns out that the weak nuclear force then turns one of the protons into a neutron by causing it to spit out a neutrino and a positron, and after that, the strong nuclear force glues, if you will, the proton and neutron together with one another. And in the helium-4 nucleus, the strong nuclear force is called the strong nuclear force for a reason. At short ranges, it's the strongest of all of the forces of nature. And so the strong nuclear force attraction between the particles overcomes the electrical repulsion. You kind of, quote unquote, you need neutrons in a nucleus because they contribute to the strong force attraction without adding any repulsion of particles. They in a sense, they attract the other particles in the nucleus with the strong nuclear force without participating in the electrical repulsion of protons for one another. And so the neutrons are kind of like the glue that holds heavy nuclei together by providing extra strong nuclear force to keep those darn protons from flying apart because of the fact that they repel one another electrically. So that's the role of the strong nuclear force. It's what holds nuclei together in the first place. And for fusion to occur, the protons, for example, have to get close enough together so that they start feeling the strong nuclear force attraction for one another and not just their electrical repulsion for one another. Any follow-ups on that? Yes?
So I understand like how it relates to the protons, but I don't understand how it relates to the neutrons.
So the idea is that neutrons and protons both feel the strong nuclear force. So a proton and a proton attract one another with the strong nuclear force, but repel one another with the electric force. A neutron and a proton attract one another with the strong nuclear force, and they're met with the electric force because the neutron is electrically neutral. So a neutron and a proton attract one another with the strong nuclear force. Electric force plays no strong role there, no particular role there. And then a neutron and a neutron, they attract one another with the strong nuclear force, and they don't repel one another electrically. So in other words, neutrons don't cause any repulsions within the nucleus, electrically speaking, but they do use the strong force to attract the other particles in the nucleus. And so they play the role of kind of like glue to help the nucleus together, because like they're the good guys that want to draw everybody together with the strong nuclear force. And so they keep those, those protons that are always arguing with one another electrically and just repel one another, they keep them together. They're like, the neutrons are like the mom who their kids want to fight and all that kind of stuff, but she won't let them and she keeps them together, so to speak. That's a stupid analogy, but I just started with that. So does that make sense? So the neutrons kind of glue the nucleus together, help glue the nucleus together because they produce strong nuclear force attraction without producing repulsion because of the electric force. Yes?
So not related to this.
Okay, so anybody want to ask anything else related to this? If not, yes?
What is the Balmer thermometer?
The Balmer thermometer refers to how the strengths of the spectral lines of hydrogen are related to the temperature of the star. So remember that we told the story of Goldilocks and the Three Stars. So I gotta find it in here. Where did I put that? Yeah, here it is. Goldilocks and the Three Stars. So Goldilocks wants to find stars with strong hydrogen spectral lines because it's my fairy tale and I make her do whatever I want her to do. So she wants stars that have strong hydrogen spectral lines. So first she went to a very hot star. And that star had very weak spectral lines of hydrogen, and so that star was too hot. Why did it have weak spectral lines of hydrogen? Because at the high temperatures, more than about, and by hot here I mean much more than 10,000 Kelvin. So O and B type stars have surface temperatures much higher than 10,000 Kelvin, for example. At stars much higher than 10,000 Kelvin, the atoms in the star's outer layers are moving so fast that hydrogen atoms simply can't hold on to their electrons, because as soon as a hydrogen atom combined with an electron, it would collide with another hydrogen atom or some other atom in the star, and they'd be moving so fast that the energy in the collision would tear the electrons straight off of it. So it's too hot for hydrogen atoms to form because the collisions are so energetic that it strips all the electrons off. Hydrogen atoms that don't have an electron orbiting the nucleus can't make spectral lines. And so as a result, you get weak spectral lines because I exaggerated. There will be some hydrogen atoms that have electrons orbiting them, but not very many, very few of them, because the collisions are so energetic that very few neutral hydrogen atoms able to absorb Balmer series spectral line wavelengths will exist in the star's atmosphere. So O and B type stars have weak hydrogen spectral lines because there's very little hydrogen in them that is not ionized. Does that make sense, or do you need me to repeat something?
No, that makes sense.
Yeah, okay. So Goldilocks says, oh, this star is too hot. So then she went to a star whose temperature happened to be a lot less than 10,000 Kelvin. And she looked and she measured its spectrum, and she could see hydrogen spectral lines, but they were not very strong. They were quite light. They were not that dark. And why? That's because that star was too cold. Too cold in that the Balmer series spectral lines are transitions where the electrons, if I want to make visible wavelength Balmer series spectral lines, the electron has to start in the n=2 level and jump up to a higher level. Because if it's in the ground state, it takes ultraviolet energies to get it to jump up into higher energy levels. So atoms in the ground state can only absorb ultraviolet light. They can't absorb visible light wavelengths. And so if virtually all of the atoms are in the ground state and a very, very tiny fraction are collisionally excited so that their electrons have been kicked up to higher energy levels by collisions, in that case, you get weak spectral lines because most of the atoms are down here in the ground state, and atoms with the electron in the ground state can only absorb UV photons. They can't absorb visible light, Balmer series photons. So Goldilocks says, oh, this star is too cold, too many atoms in the ground state, unable to absorb visible light, Balmer series wavelengths. And then she went to an A-type star whose surface temperature was around 10,000 Kelvin, and she looked at its spectrum, and it had nice, strong hydrogen spectral lines, and she was happy because its temperature was just right. Because at 10,000 Kelvin or thereabouts, the collisions are energetic enough to kick a fair number of the hydrogen atoms into the n=2 level, ready to absorb Balmer series wavelengths, but not so energetic that they strip the electrons completely off and ionize them. So around 10,000 Kelvin is where the conditions are optimal for forming hydrogen Balmer absorption lines, because collisions have enough energy to put a lot of atoms into, it's still a tiny fraction, but the largest possible number of atoms with their electron in n=2, as opposed to being ionized, or as opposed to too many of them being in the ground state. And so the Balmer thermometer, it's called a thermometer because it's kind of a way of measuring temperature, a very indirect way, but astronomers can use the strengths of the hydrogen spectral lines to indicate the temperature of the star, essentially. Now there's some ambiguity because if the spectral lines are strong, you know for hydrogen, you know that the star is about 10,000 Kelvin. If they're weaker, from that alone, you can't tell if it's cooler than 10,000 Kelvin or hotter than 10,000 Kelvin. You kind of have to choose. Well, maybe it's 6,000 Kelvin, or maybe it's 12,000 Kelvin. But when you look at other spectral lines in addition, combined, you can tell the temperature from that. In other words, the reason why the spectral sequence OBAF-GUCM, OBAFGKM, is a temperature sequence is because of the fact that temperature correlates with how strong spectral lines will be for various elements. Follow-ups on that? Anything that you need further? Okay, in that case, who's got another question? Okay, yeah, you raised your hand
Can you,
days ago, so yes.
can you describe a life track on HR diagram?
Yeah, so life tracks, also called evolutionary tracks, these are these businesses in the last chapter about stellar evolution where we were talking about, remember the HR diagram is a plot ultimately of brightness, of luminosity on the y-axis and temperature on the x-axis. And so a star at any given time has a certain luminosity and a certain surface temperature. And so it's represented by a single point on the HR diagram where the x-coordinate of that point is given by the star's surface temperature and the y-coordinate is given by the star's luminosity, the total energy per second it's emitting from its entire surface. So for example, the sun today is at this point right here because its surface temperature is 5,800 Kelvin and its luminosity by definition is 1 times the sun's luminosity. This is marked off in solar luminosities. But we know that when the sun runs out of central hydrogen and becomes a red giant, both its luminosity and its surface temperature are going to change, which means the point that represents the sun on the HR diagram is going to change. And so you could imagine, you could keep coming back and plotting the point that represents the sun at a certain time. And then you come back 1,000,000 years later and you plot it again. And then you come back 1,000,000 years later and you plot it again. You got to be patient because stars change very slowly on human time scales. And if you connect the dots, you can imagine making a movie where the point representing the sun is crawling along in the HR diagram. Not because the sun is moving through space, it's a movement of the point that represents the sun on the HR diagram. And the life track is just what you get when you connect the dots. It's the path, if you will, of points on the HR diagram that represent the star's changing temperature and luminosity as it evolves, as it changes over time. So your book calls that a life track. Astronomers tend to use the term evolutionary track for that. Yes?
Do you want us to know the life track of the low mass as well as the high mass?
So I want you to know the details of the life track for low mass stars. For high mass stars, it's actually kind of easier because high mass stars just kind of wander back and forth while after they leave the main sequence, they wander back and forth along a nearly horizontal line on the HR diagram. And unlike low mass stars, where if I know where it is along its life track, I can say what's happening inside of it. There's a nice tight correlation between what's happening on the inside of a low mass star and where it is on the HR diagram. That's nice and tightly correlated. So if I see a star on the so-called horizontal branch, for example, this is the HR diagram of the globular cluster M4, the fact that I see that this star is on the horizontal branch tells me it's fusing helium in its core. I know that just on the basis of that. The fact that this star is here on the subgiant branch tells me it's fusing hydrogen in a shell surrounding the core on its way to becoming a red giant. For high mass stars, they wander back and forth, and you can't, because they keep wandering back and forth across the same point over and over again, you can't tell what's going on in the inside of a high mass star from where it is on the HR, from where the point that represents it is on the HR diagram. So I can't ask you, to do the same thing with a high mass star that I can with a low mass star, because all we know is they're just going back and forth, and you can't say, oh, and because it's right here, it's fusing carbon in its core right now. It's just not a tight correlation with that. So tragically, I can't ask you as much about the high mass stars like that. Yes?
And does the textbook have, information like, I guess what we can read what's burning or fusing?
Oh, yeah, I mean, this figure is from your textbook. It's from your textbook, and it is telling you exactly what's going on in each of those stages. In other words, here, there's no extra picture, but what's the sun doing right now when it's on the main sequence? What's it fusing, and where is it fusing it? Hydrogen in the core, right? This picture is telling you that when the sun is here as a subgiant, on its way to becoming a red giant, it's telling you that it has an inert helium core with hydrogen fusion in the shell surrounding the core. It's telling you that when it's here on the horizontal branch, it's a helium core fusion star, in other words. It's telling you helium fusion in the core with hydrogen fusion in the shell surrounding the core, and so forth. So in other words, study this figure carefully and know that right here is where the helium flash is occurring. The so-called tip of the red giant branch, this point right there, is where helium flash is occurring. Helium flash switches it from being a red giant to a helium core fusion star, where it's a horizontal branch or helium core fusion star. Then it runs out of core helium and becomes a red giant for the second time. It becomes a double shell fusion red giant. So when it's along this path right here, it looks like this. It's got an inert carbon core surrounded by helium fusion in a shell, surrounded by hydrogen fusion in a shell. And that's what it means to say it's a double shell fusion red giant. And then instability in the helium fusion shell causes it to spike up its rate of fusion multiple times, which blows the star's outer layers off into space, and the final such produces the planetary nebula that surrounds the dead core, the carbon core, that becomes the white core final remnant. So the answer is yes, have a look at that. And if I recall correctly, there's also a mastering astronomy thing that goes through that stuff too. I'm trying to remember, because I made the assignments months ago, so I don't remember the details. But anyway, so yeah, that's all in there, for sure.
Oh,
And the other thing is that link there is also very nice. It describes everything.
I
Yes?
think when you touch the cord, it changes the color of the screen.
Oh, yeah, right, yeah.
Yeah.
Because basically there's pins there, and if one of them pulls away a little bit, then it stops losing some of that signal. And it's RGB, red, green, blue, and so if one of them loses strength, it changes the color. So I've magically made it correct colors again.
I
So
know, you're a magician. I saw you go do
That's
it
right.
back and forth, and I was like, wow, magic.
yeah, that's right. I want the colors to be good, and it works. Yeah.
Oh my god, it worked.
Right. Yes, I have another power. I'm going to have an observing session, and it rains. So I control the weather by scheduling observing sessions. I cause clouds and rain.
Yeah,
I have not decided yet whether to use that power for good or for evil. So I'm taking advice on that. Yes.
My question has nothing to do with that.
Okay. So we're going to move on to the next topic, or no? Okay. So no, you got to follow up. Yes.
Does the helium flash explode the outer layer?
No. So the helium flash takes place right here, and it turns out that the weight of the layers above it are high enough at that point that it contains the helium flash. You don't see anything immediately on the outside of the star when the helium flash occurs. So in other words, there's nothing to tell you on the outside, wow, that star is undergoing the helium flash. What happens is it only lasts for a few minutes, and when it's over, the core expands and cools down, and so gradually the star starts shrinking and raising its temperature, and so on a humanly long but astronomically short time scale, it changes from a red giant into a horizontal branch star, into a core fusion star, a helium-core fusion star. But you wouldn't see that on the outside. You would, if you were watching it, you know, this helium flash lasts only for a few minutes. There's nothing you could see on the outside of the star that would tell you the helium flash is occurring, it turns out. Yes. Okay. All right. Yes.
The famous formula E equals MC squared.
Yeah.
What does that play in explaining how nuclear fusion?
Oh, so remember we said that the net reaction is 4 hydrogens become 1 helium plus energy.
Yeah.
And the idea behind E equals MC squared playing a role here is a helium nucleus is about 0.7% smaller in mass than the 4 hydrogens that fused to form it. And that mass, in fact, is turned into energy. So a star is using nuclear fusion reactions to shine, and ultimately, it's turning mass into energy. The light coming off of the sun is reducing the sun's mass. It's losing mass because of the fact that it's giving off energy, and that energy is ultimately coming from the nuclear reactions, where each nuclear reaction is converting some mass into energy. And E equals MC squared says the energy you get from a mass, if you convert mass m into energy, you have to multiply it by the speed of light squared to see how much energy you got. Which means a little bit of mass makes a lot of energy, because c squared is a very big number. Yes?
So I have a different question for this.
Okay.
So should we expect like every single type of quantitative problem that was on mastering astronomy?
Not if I want you to be done with the exam before 8 in the evening, no. That's what I would say to that. Yeah. No, you're not going to see every possible type of quantitative problem in here. And I do have I have a tendency to, on the exams, want you to be able to do things like, okay, if I got twice as far away from a star, what would happen to its brightness? And then you remember, oh, well, it involves the inverse square law, so if you double the distance, you have to square that and say that it's only 1/4 as bright, for example. I like those kinds of quantitative reasoning problems because you don't need a calculator, and I can give them to you and test if you're developing quantitative reasoning, and get the exam from you before 8 p.m., which is not my goal, is to wait until 8 p.m. for you to finish your exam.
So will we have formulas just like last time?
Yeah, if you need a formula, I would provide a formula sheet. Yeah, I don't expect you to memorize like all the formulas, no.
And will there be any type of problems that involve conversions?
I'm not planning to have you like convert from meters to kilometers or stuff like that, no. Sad but true, I'd like to, but I'm not. And I know that's probably gonna cheat you on this, but it's no.
Thank you.
You're welcome. Yes?
One of the questions said to understand why S equals luminosity divided.
Yeah. So why is brightness luminosity over 4 pi r²